Welcome. This is the first in the series for the Category 8 Green Ecosystem for Sentinel Connectors. I'm Dr. Brett Robinson. I am the designer of the jack and helped in the cable development for the whole ecosystem. So at this point, we're going to talk about the path of least resistance for data and power transmission. So what exactly is the path of least resistance? Well, to engineers, it means many different things, especially mechanical and electrical engineers. And it's important to understand that while they're different, in many ways, they're exactly the same. So for instance, if we're talking about water, it's the resistance of the water in motion through fluid to an alternative side path. And everybody goes, well, what the hell does that mean? Okay, what that means very simply is if you have a garden hose, and it's a 1-inch garden hose, and you take and put on a 1/2-inch nipple on it, then your volume changes from 1 inch to a 1/2 inch. Now, the 1/2 inch gives you least amount of volume, lessens the volume, but it increases the pressure outward, right? So now you have a path of least resistance, right? Before, when you had just water flowing, you didn't really have much pressure behind it. Then the next one would be a thermal bridge. So what's a thermal bridge? Well, a thermal bridge can be called a cold bridge, a heat bridge, but basically it's placed on circuit boards. And what it does, it's a place which pulls in higher thermal conductivity. So rather than your copper board overheating or the components on the board overheating, this thermal bridge, it pulls all that into it and transfers that into heat. So that allows less heat coming out of the components. And again, that means a path of least resistance. Now we're going to have to be speaking about conductive copper and copper wire. And there's a lot of arguments about what is and what isn't. The commercial world likes to think they're different than the military world, but the military world really has been doing this a lot longer. And basically, the rules of physics stay the same. The higher conductivity for copper wire is its length and width. Now, I understand that weight comes into an issue in the commercial world, so they try to make the wire smaller. The trouble with that is when you make the wire smaller, the wire then becomes your resistive bridge. That becomes your resistor. And the greater resistance, the higher thermal activity. And if you put it in a bundle of wire together, let's say they're 28 gauge wire, and you're pumping an amplifier through there because you're trying to get the data down and push it through greater lengths, what happens is that bundle of wire then turns into, well, basically a heated mess like light bulbs, and it melts. The same thing happens when you're trying to prevent lightning from blowing a hole in the ceiling of your house. So you have to give lightning or any high source of transient energy a path so that it doesn't affect the house or the people inside. And the way you do that is you place a lightning rod up on the roof, you put an 0.0 gauge wire off the lightning rod, you bring it down to another copper or aluminum rod that's in the ground 8 feet, and that becomes the path of least resistance, the path that's easier for the transient energy or lightning to go through into earth, ground. And earth ground is the predominant way you want to do it because the earth itself will absorb all of that transient energy. There are 3 components of copper wire to transmit data or flow power, and they are wire gauge, weight, length, equal more or less electrically to are measured as resistance inside the copper wire. A short wire always has a lower resistance value than a long one. But electricity always takes the lowest resistance path. So in every path available to it, you always want to provide the lowest resistance path to make your job easier, to make your transmissions easier, to be able to put amps, watts over that same wire of circuitry. And when your computer, for instance, takes the path of least resistance, it's called a dead short, of which all of us have had. Resistance is always directly proportional to the length of the path through which current flows. So, simply put, the longer the wire length, the more the resistance. The smaller the wire length, the higher the resistance and the decrease in flow. So if you go to smaller wires, basically, to make it simple, it's harder to get amps and watts for power down it. It's harder for getting power down it. And what you end up doing is having to put an amplifier of one kind or another to push it through. And that's where the problems start. You start to expend calories and heat. And that runs into money, especially in data centers. Now, as you can see here, there's a table of resistivity and conductivity at 68 degrees Fahrenheit. I don't really want to get into all of these, but basically when you see them, I did them in the material that works the best for what has to be laid out on a board, on a printed circuit board. Silver is your best path. Now, I'm not talking silver like you would get like Indian silver, which turns black because it oxygenates. I'm talking German silver, also known as sterling silver, and that truly is the path of least resistance on a circuit board. The next one down is what you would think it would be. It would be copper. The next one down from that would be annealed copper. And then you notice that things that we love to cover our boards in because we're worried about, I don't know, moisture, heat. The gold works okay, but it's lousy transmitter for, Nickel works great, won't corrode. Platinum is really great for temperature. It's really great for protecting your copper board. Tin is a thing of the past. Tin is okay to mix in with lead, but the trouble with tin is if you have to use it for anything that goes into space, tin will grow 50,000 times bigger than what you put into it. When they started opening up the Sputniks, they found out that the reason they crashed was that the tin had grown in there like a forest and shorted everything out. Lead is a good substance for soldering, but it's absolutely horrible for if you want to put current through it because it melts. It's resistant. It resists the temperatures and it will melt. The one we want to talk about is stainless steel. Now, stainless steel is great if you're building a structure, if you're building a knife, if you're building parts for your car. But stainless steel is lousy for temperature control, and it's 200 ohms, so it's really lousy to make shield material out of, because if you have a shield, it has to be less than 2.5 milliohms per the mill standard, and you'll never get there from here with stainless. Next thing we're going to be talking about is mill standard 202G, and I'm not going to spend a lot of time on it. It's your bonding and grounding measurements. Like I said, I work with the mill standards. They've been there, they've done that. They know what it takes to do for bonding and grounding. I don't have to go to some commercial TIA spec, IEC spec. I don't have to go to anybody's specs because the commercial specs have allowed companies who pay the biggest amount of money to give them the biggest break. The problem with that is you have problems and you say, well, it's just how it is. No, it's not. You haven't paid attention to the math and you haven't paid attention to the science. So what you need to really measure the equipment and prove that you're less than 2.5 milliohms on wire mesh, on a shield, on your materials, on copper, on gold, etc., is that it should be less than 2.5 milliohms per square inch. If it's not less than that, and you're getting up into the ohms range, well, then your resistance is getting so high that you're actually losing power and data because there's way too much resistance there. And for that, the best way to do it, like I said, is a 4-wire milliohm meter. I prefer X-Tech. I'm just using its name. They've been out there forever, and they're affordable. Now, you're going to be looking at a chart at this point for EMI, EMC, transient energy. And what I'm finding in speaking with a lot of our clients, or a lot of people, there's an argument out there. What is ground? Well, there's only 2 grounds that you can say that are ground. The negative side of the battery and the earth itself, earth ground. Now, there's guys out there who say, well, no, the green wire is ground. No, it's called a safety ground. And that green wire back in your box has absolutely nothing to do with grounding your unit. It's hooked to the neutral line, and the reason it's hooked to the neutral line is if somebody's getting a shock, it will cause that trip to open up and not kill the individual who's getting fried by doing something dumb with a screwdriver in their hand or whatever they decided to do that made no sense whatsoever. Now, if you're going to have to use that, let's say there isn't any other ground to use, you don't have a water pipe, which makes a great ground because water runs through it. And I'm talking a copper pipe, not a plastic pipe. Then you can put a 500 milliohm inductor between the green wire and the chassis ground for the unit, which is supposed to also be at the other end to get chassis ground hooked to earth ground. Now, if you don't have earth ground, remember, you can always use the minus VDC on a battery or some other device that gives you DC. So if you have some device that's going to give it to you and you have DC coming in, there's the red and there's the black. The black is ground because it's DC ground. Then you can use that as ground. If you just have power, you have no ground. So in that case, then you have to have chassis ground, and chassis ground by itself is just your chassis, so it really doesn't provide a ground. So then the chassis must hook to some sort of a copper plate or something that is going to allow it to be hooked into earth ground. Bonding, grounding, the basics. This one turns also into, we kind of went over some of this already. We're already discussing some of this, what I'm talking about. But in the world of EMI, EMP, especially in the world of EMP, EMI, transient energy protection, and that's anything from EMP to lightning mitigation, you have to have a path to ground, and in this case, earth ground. And the only other way that can be achieved is not through a resistor, which resists, but it does nothing to stop it. It has to be a TVS, a transient voltage suppression device, also known as an avalanche diode. And what this avalanche diode does, kind of think of it as a switch. When it's set for so much voltage and so much current, it will switch, flip, and then pass the over voltage to ground. Using other kind of devices out there don't really work as well, because once they get too much over voltage, they unfortunately pass that back into your system, or they become a dead short. And if you have some sort of device in an aircraft, the pilots get a little touchy about the fact that their equipment just blew out. And you say, well, I put in a resistor, or I put in this, I put in that, I put a metal oxide varistor there. But all those things go dead short. An avalanche diode, especially one that's bidirectional, it tends to open. I'd rather have it open than a dead short. A dead short will take things with it. Next. Circa 1970, Bell Labs thought they had the answer to cable shielding. And in those low frequency days, well, they were more interested in ground loops or ESD. But then if you're in the kilohertz or the hertz range, their methods worked. Crossing wires over each other, what have you. Today, in the 21st century, not so much. The world has changed. You can't go by the old Bell Labs days. There was nothing wrong with them. They were where they needed to be at the time. But today we're looking at frequency ranges that go up into the terahertz. And so shielding becomes an active device, something that's necessary to have. Saying that you can't measure shielding or there's no proof that shielding works, etc., 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 is just plain poppycock. It's someone who just doesn't want to do it. In this case, I go to the MIL standards. And the MIL standards are 461G, MIL standard 464G, RTCA DO160G. Now that is the FAA's version of the MIL standard. It's used a lot. It's the same thing used in Europe, RTCA DO160. It's used over there. All of those are derivatives of the MIL standards. Everybody likes to just give it its own name. And then you have MIL standard 188.124C, and that has to do with EMP. And that has to do with effectively shielding your equipment, which we call red and black, and I'm not going to discuss it in this particular video, from people listening from an outside source. I have done work with Sentinel. We were over at the base in Alabama, and they were having people going through that base, actually getting information when we were told by 3 initial groups it was impossible. It was not impossible because they didn't do 3 things. 1, they didn't shield the cables. 2, they didn't shield the building. And 3, they didn't ground it right. So the bad guys were actually sitting in cars and getting in all the keystrokes, and they were wondering how things were getting through. It happens in hospitals a lot too, in the commercial side. You'll see somebody walking up and down the halls you don't really know. You think he's talking on his phone or listening to music, and what he's really doing is looking for the part in the wall that allows him the greatest access to where patients' data is being transmitted, and all they're doing is standing out there, pulling in all that information through the cables, leaking it out via RFI, radio frequency interference. Now, shields are screens, and in England, a screen is the same as we would call in this country a mesh screen or an aluminum foil screen. And they come in various types. They're going to come in 60%, 75%, 100% would be naturally aluminum foil. For the shield to work, whether it's single overbraid, double overbraid, it has to be grounded. It has to be, the connectors that hook to it have to have a shield on them. They have to be attached to those inner shields in a 360-degree manner. You do not attach it to, if you happen to have one, your ESD flow little wire in there, because that is really, in the real world at high speeds, an antenna. If you want to shield, it has to be grounded at both ends. If we were dealing in just the kilohertz or hertz range, you could be shielded at one end. But the fact of the matter is, shields don't absorb energy and get rid of it. Where is the path? There is no path. It doesn't absorb it and magically put it somewhere. What it has to do is have a path, the path of least resistance, and that is ground. So now we're going to talk about the basic model for how to properly lay out a 6-layer board. We go, why do I care? Well, the problem is with most guys when they're laying out a 6-layer board or a split pair board, they don't really take in line crosstalk. And so what's happening is they try to do it on 1 or 2 layers and it's not going to work. So what happens is you start having the lines start talking to each other. So the way I do this, and I find it the best way, is first I don't use FR4. FR4 is an ancient board material. There are other companies out there that make what are called femto boards, where instead of fiberglass in between, they use Teflon. That forces them to use pure copper for their lines on top. And you're going to need a 6-layer board, and the reason why I'm saying is the top layer will have four paths. Then there will be a chassis ground or earth ground. You'll have another path for 2 wires to go on, and then then another chassis ground or earth ground, and then you'll have another path for 2 more wires to go on, and now you have ground. So what you have is numbers 1 and 2 for a split pair on the top, 7 and 8 on the top. The next middle sections, which is separated by a ground above it and a ground below it, is 3 and 6, which is your split for split pair. Then the final layer is ground, and your third board level is numbers 4 and 5. Now 4 and 5 and 7 and 8 can be used for transmitting power on. So you want those lines separated because power talks to itself. So if you put 2 plus powers together and 2 negative powers together, they're really not doing what you wanted to have. What you wanted to have was power and return on the same path. And that helps you for EMP, because the power will try to find a path to go to, and the ground, which is your return DC, gives it the path to return back to. Now, all of these have to be 50 ohm transmission lines. If you make them 100 ohm, what will happen is your path will be too high in ohm, and it doesn't work. And you go, I tried what you said, but I still had EMI problems. So these paths have to be 50 ohm paths. Fun facts to discuss. Why? Because you need a break from all the other dull stuff I've been telling you. So, and this is really interesting, there's over 1,800,000,000 world ports connected in the United States, the UK, the EU, Asia, Africa, plus all the island nations. That is a lot of data ports, and if all these places are spending about $5 million a day to pump power through that, you're looking at a ton of cash and a ton of expended energy you didn't need to spend. The data infrastructure has seen great advances in the past 20 to 30 years. However, one place that has very little been done in advancement is the PC board, the jack connectors, the plug connections, the shielded cable, and the wired gauge advancements. They've been argued about so much that it gets stymied. And the problem is, it ain't that hard. The laws of physics are still applying no matter what you do. They're really not that hard. I realize there's politics involved because somebody just doesn't want to do it, but the fact of the matter is, it's not this hard. Although chip technology, for instance, has advanced with NVIDIA, AMD, Intel, battling for greater processing capabilities, well, this has done little to help reduce the global strain that has been put on energy and power consumption. Primarily because everybody still insists on signal amplification, because they put all of these inductors and capacitors and all these things in there because they didn't build it correctly. And now to get data and transmission down it, they have to cram it down and push it into it. Well, this white paper document has clearly established a delineate path for the success for energy efficiency and its infrastructures, which enables higher data availability while lowering power consumption. Thus, the green in the title. The advanced solutions have been created have a dual purpose because it incorporates EMI, EMP, transient energy protection. The cutting-edge design also assures data infrastructure prevention. It doesn't allow for RFI intrusion. And the stripline design that we're using in all of this doesn't require components. Components are the main problem when you're trying to save energy because no one component is just like the other one. But when you do it in stripline, the components between two grounds to make this shape, which is usually a resistor, an inductor, and a capacitor, are directly controlled. They don't change. So to do all this, this is called the green infrastructure of the future. So to incorporate a true path forward, electronic design features still have to incorporate a solution which must establish a one-time monetary expenditure onto infrastructure with a clear return on investment within a 3-year period. What does this mean, right? It's a lot of words. It means whatever you're going to do today has to be able to return the money to you in the next 3 years so you can go on to the next thing. But if you're spending $5 million a month on expenditures, you're not moving forward at all. In fact, you're going bankrupt. And your equipment is getting worn out through heat, through exposure, through compression because you're using amplifiers. And all of this is reducing your ability to make the profits, and that's what it's all about. So for the revolutionary solution, and it really isn't that revolutionary, we have designed and patented an RJ45 using stripline. Now, that same stripline technology was used in the days when I was developing aircraft search and track antennas, where we couldn't use components, so we used stripline. And it goes back, now this is interesting, it goes back also to Ma Bell in '57 because they're the first ones who actually used stripline. The problem was back in '57 and all the way up to the beginning of the '80s that its development and equipment to make it work properly really didn't exist very well, actually. So today, we can easily be at 5 gigahertz, 10 gigahertz, with the same transmission devices that allow us to get on because of cable shielding, because of uniquely designed PCB materials, because of uniquely designed stripline connectors, uniquely made shields. All of these give you the green that you need. Not only is it money, but it's green because the government tells you, we have to do everything in green. We need to be saving energy. Well, this is the only way you're going to do it. If you keep doing it the way you've been doing it, it's not going to work. And yes, there are plenty of femto-based circuit boards available today that you can use. But we're not going to discuss the manufacturers at this point. But having my office in Arizona, it's pretty interesting because the basic 2 companies that make these are based right here in Arizona. Commercially available data communication transceivers and standard cabling links performing today have kind of reached their capacity. So the answer has always been, well, we don't have to worry about copper anymore because we're going to go with optical cable. Well, it turns out that optical cable, unfortunately, takes more power to run. It's not very efficient, although you've been told it is. We no longer use glass, so if you're hit with EMP, the cable then becomes opaque because the plastic turns white. And your transmission and receiving devices on optical cable, even though they're supposed to be hardened, nobody wants to spend the money to do it. So if your transmit and receive are dead, you can have all the fiber optics you want, but you're not going to be able to transmit through it. The answer truly is, for energy, is still copper. UTP cables serve a limited purpose, but they serve them very well. Shielded cables, on the other hand, offer the possibility of going much farther in distance and way faster while using less power, so it takes less amplification. Data cabling infrastructure has seen great advances in the past 30 years. The next big focus area for data communication technologies is energy efficiency. Up to and through 10 gigabits Ethernet over CAT6A, unshielded cables used connectors with magnetics. Now, magnetics had a very good purpose, and they've served their purpose. When you were in an area of kilohertz, low megahertz, they worked great. The trouble is today, as you're trying to go through higher speeds, they are the main reason you can't get past 300 to 500 megahertz. And later on, we will show you some data that absolutely proves it. Now, does it mean that those connectors don't work? No. It means that they're working for what they were designed to do. But if you're trying to take them into an area where they're not designed, you're never going to have enough power to push through all of those inductors, all of those formatted energy sucking things, and be able to get data out. There's never going to be enough energy to pump in there. Like one guy called me one day, he said, my RJ45 melted. It melted because he was pumping up so much energy to get to the higher frequencies. He literally overheated the plastic because the inductors in there became more like light bulbs and they melted it. Now, for 25 gigabits per second, Ethernet over CAT8, shielded cabling along with PCB materials, the upgraded RJ45 stripline connectors, cable, cords, assemblies, using real-time shielded connectors and different upgraded technologies like stripline, and using better and proper grounding methods, eliminate the need for copious amounts of analog equalization and digital signal processing. You're going to get rid of a lot of that. You're not going to need repeaters. You're not going to need any of those because you have the path of least resistance. This allows you to go from 500 megahertz to 3,000, 5,000, 10,000 megahertz with shielded transceivers that will then channel their energy, and they're more efficient for moving signals and data forward. The downside is, if you want these same things to be working in the old school days at 10 kilohertz or 5 megahertz or 10 megahertz, it's time you change your mindset. You can't go backwards to go forwards. You can't use the old school stuff to do the new school. Will they work? Yes. But if you want to go faster, then the world has to change with it. If you want to save energy, you have to change the way it's going now. So, how far, how fast, and at what cost is this going to put us back? Reach. What does that mean? It means that the rate and bit error ratio depend on the channel signal to noise ratio. Okay, and you're going, and? Well, the shielded cable basically enables us to go farther, faster in 3 different ways. It improves energy efficiency. First, by the shielding cable having less loss. In other words, you're not going to be transmitting EMI out. It's going to stay within the cable. It also provides a real path circuit for common mode noise reduction. And that's really, truly important, because that common mode noise is what destroys your data communications. Third, the shielded cable further isolates internal signals from external noise. In other words, put it simply, the gazoutas don't get gazintas and the gazintas don't go outa, as I used to tell my classes over many, many years. The same shielded cable principles apply to shielded connectors, and thus to shielded cords installed in cabling links. Moreover, the effectiveness of shielded cabling is greater at higher frequencies. So as we get up into the gigahertz range, the shield becomes more and more effective. But that means you can't just float it. It means you have to pay attention to the laws of physics that makes it work the way it needs to. What about power delivery over data links? Well, copper data communication systems now have additional means for delivering power together with data. Both power loss and signal loss are proportional now to DC resistance. These same properties that make a cable link better for data signals also make it better for power delivery. The mag jack versus CAT8 stripline jack versus optical cable fiber. So what you're seeing here with the mag jack, and again, I am not knocking the mag jack, but it was designed for a particular time in data communications when EMI was your biggest and worst enemy and you were at lower speeds. And if you look at the schematic here for the mag jack, you'll see, all these inductors in there. And what you're really seeing is all the tech that is trying to reduce crosstalk. But to get past all these transformers, to get past all these resistors, to get past all these capacitors, it takes tremendous amounts of energy. So as long as you're using these below 300 megahertz, they work just fine. But if you're going to try to use them for anything above 300 megahertz, well, the power and data diminish due to inductive transformers. And that's just the laws of physics. And you can't get away from that. This, basically, the next information you see below this is what you're really seeing is my testing data of how I figured out what, if I'm testing, for instance, at 42 volts DC, 1.5 amps, why is it that I wasn't, whether I'm using my jack, which was the CAT8 jack, or this jack, why was there a difference in amps? Why is there a difference in ohmic resistance or electrical resistance? And it is basically simply power. If I'm using less power, I'm not wasting and turning it into calories or heat. All right, at this point, we're up to the CAT8 25 gig shielded stripline jack, which is patented. What you're seeing here is a basic schematic of stripline. And you can see inside, you can see the shapes. And those shapes create what's called an LCR circuit. And that circuit is then layered out into 6 different layers. And that in turn gets placed actually inside the jack. And as long as the jack is grounded, EMP doesn't bother you, EMI doesn't bother you. None of the transient energies don't bother you. So you truly have now at this point the path of least resistance. You have all the components drawn in between the PCB, the DC return, and the earth grounds. The energy efficiency saves over 75% in energy costs. Higher speeds, 25G, 50G, and 100G, are all very achievable. It just takes it's just a matter of just changing the figures, the mechanical figures in there, no components, and I can tune it to anything we need to. The applications at this time work up to 3 gigahertz per pair in an RJ interface package, which makes so you're not getting away from the standard interface package. I do have to tell you though that it is a tab up. It has 4 shield grounds, and that the numbering, the 1, 2, 3, 4, 5, 6, 7, 8 are reversed because it is a tab up. This technology is presently actually being used in 360,000 units by major test equipment manufacturers today. In fact, it's the only one they actually trust to get them up to the speeds where they need to be, and that's all over the world. And as you can see, you'll see what the item looks like. It's a CAT8 jack. We sometimes call it the 25G jack because it's basically designed for 25 gig. What you're seeing is the differential. The differential between the differential and a split pair is really quite simple. Differential is 1, 2, 3, 4, 5, 6, 7, 8. Split pair is 1, 2, 3, 6, 4, 5, 7, 8. Now the truth is you don't need to do a split pair jack. We do have some companies that insist on it, but quite frankly, once you have the wiring put in correctly, once you have your board built correctly, a differential jack works just fine, so you can use it differentially, or you can use it in split pair. Pins don't know what they are. They only know what goes on them. I've had guys argue, well, how will that work? Well, a pin doesn't know what it's on, and as long as you have your board set up to handle split pair, a differential jack just puts it out to where it's drawn on your board. Now the next one is fiber cabling. And I have to be careful here because over the years you've heard lots of things from the people who want to push fiber rather than copper. The truth is fiber is none of the things that they claim it to be. It was at one point when it was using glass, but today they use optical plastic. And optical plastic has its problems. In fact, your losses now, your power losses are greater than on a copper wire. Because you remember, all you have to do is just increase the width of that copper wire from, let's say, 24 gauge to 20 gauge, and now you can go miles, and you can handle 200, 300 watts, where on an optical cable, you're limited. Also, due to the optical cable having a transmit and receive, it uses higher wattage, and its peak intensity in single mode fiber, well, you start to then have losses. Some example is the bend of the fiber due to dirt or, over years with the connector wearing down. And then, when that happens, then you start having dramatic losses, and then you have to go find it. Where with copper or a standard jack or a standard plug, it's easier to find very rapidly. The energy lost is about 0.01 diameter, and it causes the fiber to heat up. Now once the glass, let's call it, well, we've been calling it glass for years, but let's call it what it really is, plastic. So once that plastic heats up, you lose energy. You start to have what's called a fiber fuse, where it links and burns out. Since a multi-mode, for instance, fiber core is much larger, typically 0.05 millimeters or larger in diameter, the higher the wattages can be carried on it. But you need to worry about that because those powers can go up from 20 watts in a single mode fiber to 100 watts in a multi-mode fiber, And if you're having also a transient event like EMP, that creates the plastic turn white and it blows out the transmit and receive. So now all the things you were told, oh, it's this, it's that, are not true. It's pushing, they're trying to really, what they do is push an adaptive system, which the Navy, the Air Force, and the Army are getting rid of, because under high signal data rates, which is about 20,000 volts per meter, optical cable starts to die. It starts to become opaque. And because the manufacturers decided not to do EMI and EMP, and we're not going to name who they are, on their transmit and receive devices, what happens is that high energy then blows those out, and now you don't have anything to transmit data over. So the last and more important thing we need to talk about is cable hybrid adaptions for both commercial and military. Basically, when you use copper, it gives you the opportunity to mix and match mil-circular connectors with plugs, with jacks, with single power outputs, which generally the companies where they fly a lot of these hybrid little toys for snooping, they all use a hybrid cable. And the cable allows you to actually take power and use that power on a hybrid cable to power up multiple units, as much as 4 to 6 at a time. This next area you're looking at is the cable shield verification test. It was designed and built off of MIL Standard 461G. MIL Standard 461G tests all sorts of cables, harnesses, and shields. They've been doing this for about 75 years. So I've basically adapted it and have given up on listening to too many demonstrations by too many people on the commercial side who are great theoretical engineers, but unlike myself, who's got 40 years of hands-on, they don't have that. And so they're speaking in a way of, well, if we could do this, we could do that. The truth is, it's already been done. You don't have to reinvent the wheel. And that's what we do here. So next thing what you're looking at is a standard CAT8 cable, no shielding. And what we did is we tested it. And the reason I did is because actually there was a shield, but I never attached the shield to the back shell of the plug. And so the myth that's been placed out by many companies telling you, oh, the shield absorbs all that energy. Well, here's nuts proof, full-time reality is all the EMI you're putting out. For instance, I'm going to look at this for a second here. At 73 megahertz, 121 megahertz, 142 megahertz, 194 megahertz, and 243 megahertz, you're putting out close to 30 dB of noise. Now that's not good, because in a bundle, each one of these then talks to the next bundle, the next bundle, and the next bundle, and you start having tremendous data losses. So here what we see is an Hitachi Tempest cable. Hitachi was a company that was coming to our lab quite often, and I was doing a lot of their shield verification tests for them. And they said, could you build a Tempest cable? And we said, sure. Because we were told it couldn't be done. Well, it can't be done if you don't do the right methods. And they come out of 464G, how to do it, how to build it. And so we were able to build the very first Hitachi Tempest Class 1, which that's what it's called, Class 1 shielded cable. And it passed completely 100% EMI, EMP. And as you can see in the actual test, you don't see any of those little squigglies, as the guys call them. It's because there aren't any. There's nothing leaking out of those cables. And those cables, by the way we assure that they can't leak, they're seated in chambers that are grounded, right? So instead of having a big EMI chamber, we actually have smaller chambers that are sitting on ground planes, and those ground planes are hooked to earth ground. So you can't get anything out of them. Now this is a CAT8 quablum cable, which we are now designing and working for quablum for, to get theirs to meet or to be an exact copy of Hitachi's. We're getting there little by little. In fact, they're telling me now that they have one that they feel really will match with the Hitachi's. What was nice to see was using the CAT8 plugs and jacks, even with a slight outage at 140 megahertz at 10 dB, which is really kind of small. Under most conditions for commercial, you wouldn't care. We didn't have an outage. And so initially, the tolerance level for EMI met, EMI and EMP is really met. The 140 megahertz being out at 10 dB again, it's so low that there's probably a good chance that it may not be affected by any of it. The better thing is if you can get it darn quiet, people can't sit outside your building and look at your keystrokes coming out of your CAT5 or CAT6 cables. What you're here is seeing what the chambers look like on the inside. This is a CAT8 chamber. One side is the Hitachi and the other side is the quablum. And your tuned antenna in the middle. So what you're looking at here is on the left is the Hitachi Tempest cable with the H shielded plug on it. The right one is the quablum cable with the CAT8 plug on it. And that is a shielded plug, a totally new design that can get you up to 5 gigahertz. In fact, it's the only one right now, I believe, that on the market that can. And that, even with the cable not being exactly perfect, it helped tremendously in reducing noise. And EMI, you need to reduce that. And EMP, you definitely want something that's going to shunt it off to ground so that you're not blowing out your equipment on the inside. What you're looking at now is in our test setup is our new equipment from Rigol. And this allows me to do multiple test tasks with one unit rather than multiple units. So what you're seeing here at 102 megahertz is the eye, which is completely open. You're seeing the actual frequency coming in for the O-scope, and you're seeing an analysis coming in on how the data looks like coming in through a network analyzer, all in one unit. So right now we're looking at 102 megahertz, which is at the center frequency. And what this is showing is the eye is open, it's collecting data, and it's operating the way you'd like to have for a CAT8 connector. This one here is where we expanded out. I wanted to see the eye, a close-in of the eye. I was putting in 800 megahertz of RF energy, and I wanted to be able to see how much it's reduced the eye. A lot of the military side, as they put it, they don't want to understand, they don't want to learn what the squiggles mean. They don't care. But when looking at an eye tells you very quickly whether data is going forward and back. So what you're seeing is the data going in and the data coming back. You are then seeing the frequency of the energy being projected in RF energy going in at 5 milliwatts. And so you see that the CAT8 jack is absolutely handling the data going in and out at 800 megahertz. So what you're looking at here is two different things. This new unit gives me the opportunity to look at the energy that's being expended as it goes through the cable. And it also lets me look at it in comparative to how it's reacting with the connector. So on the left side, you're just seeing 5 milliwatts going through on the O-scope. On the right side, you're actually seeing the projection as a network analyzer would project it, so that you can see the flow of the energy and notice that it's continuous and harmonious from 40 megahertz all the way up through 800 megahertz for a CAT8 jack. What you're looking at here is the RF signal proof. Now on this, I'm using a spectrum analyzer, And all it's telling me is you are truly seeing these frequencies coming through. And of course, where the frequencies are similar on a spectrum analyzer, they do what's called blooming. So you see these tall lines, these squiggles, but what they're just really telling you is that it's summing that energy together at that level. At some level, it actually has reduced the energy down to a very low amount, and as you see it peak up towards the other end, it's showing you the proof that you are looking at 40 megahertz to 2 gigahertz of signal proof at 5 milliwatts. What this is a picture of the generator that we were using, a true RF generator. You can't bring it up too high, or higher than 5 milliwatts, because that energy would be a lot for a lot of equipment, especially anything that's an O-scope or other spectrum analyzer. You can burn out the front end. So what you do is you're showing that you can get it out there, but you're reducing it down in height. You also want to prevent clipping. So it is showing two things. One, you actually do have energy coming out. You are really running from 40 megahertz to 800 megahertz. And that is required by any standard spec. This one here, we had done a CAT8 RF energy at 420 megahertz. One of the questions was, since I'm running my cables at 6 feet, and the average connector usually runs around 400 megahertz, they said, well, what does the eye look like for this particular unit? So this CAT8 jack, first of all, on the left-hand side, you are seeing the proof of the energy coming down, being transmitted down, and it's an S pattern. And on the right, you're seeing the eye. So at 420 megahertz, the eye is absolutely clean, coming down a 6-foot cable through a test board with a CAT8 connector on one end and a receiver test board with a CAT8 connector on the other end. The parts that you see there, well, what's on that board? Those are actually 50 ohm loads, because we're looking at one particular line. And so when you do this, you have to balance the board out. So any line you're actually not testing, you have to put a 50 ohm load on that. So what you're looking at here is how you're supposed to lay out your cables in split pair for power over Ethernet. Well, the one on the left is the one that they're using as a standard, but the standard was actually made in '57. We're in the 21st century and things have changed. We're not in the kilohertz and hertz range any longer. So the reason I say that the split pair and differential are incorrect is because they're putting the two pluses together, two minuses together. They're having to transmit and receive not in the right path for protection against energy. The one on the right, if you want to worry about EMI and you want to worry about EMP, then you need to take advantage of the fact that the way to do your layout is you have your transmits plus and minus, and then same thing with the receive is plus and minus together. On your differential side, you want to use that minus, the minus VDC and minus DC, rather than having two pluses together, two minuses together. You want that negative in between, because that is DC negative voltage, that DC voltage, the return voltage, actually is a shield. And if you're worried about transient energy getting in on your cable, laying it out in this pattern allows you to use that ground to shield against anything coming from the outside. So the outside world, if somebody's pushing energy at you, especially if you're on shipboard or in the military or you're in a commercial bus or vehicle where there's energy coming at you, or even on a train where they're constantly sending RF energy to you for signals, you want to be able to have your cable so the cable truly can't allow that energy to mitigate, to get all through it. So you want to mitigate it in a way that it allows it to be equaled out, and that's why you're laying it out there, and that's why you have the two sides, one saying power over Ethernet incorrect way, and power over Ethernet the correct way. And they have to be done in the correct way. And I know your guys are out there going to say, but the TIA says, but the IEEE says. The truth is, you don't care what they say. The truth is, they're organizations that don't have teeth. What you need is to be able to know that you're doing it per the spec that you signed up to do, whether it's commercial or military. And if EMP or EMI or RFI are in that spec, then I don't care what they tell you. You have to do it the right way. The right way is to, one, lower costs when you do it, which the correct way does lower that. You don't have to put in capacitors or inductors. You don't have to add anything because you have the path of least resistance. The path of least resistance says the grounds, the energy goes to ground and it goes to earth ground, not the green wire. I'm going to say that again. The green wire is not ground. The green wire is a safety wire. The green wire is attached to neutral. And I've had guys argue with me, say, well, yeah, but it's 0 volts. No, it's not. If you actually measure the neutral line, at some point it's high, at some point it's low. The reason they called it 0 volts about 75 years ago is they didn't know what else to call it. They didn't have a name for what they were seeing, so they called it 0. Well, it's not 0. It does allow for toggling if somebody's being electrocuted, but it doesn't help you when you're trying to ground something. In fact, it increases the noise. That's why your TV sets, your LED TVs that you're loving, and your UHD TVs, you notice it's 2-prong now. It's not 3-prong. The 3rd prong came off the neutral line. That was making it so you couldn't see your screens. So they went back to the old way of the neutral line and the hot line. And that's what's keeping it stable.